everyone, my name is Chandan and I am from Indian Institute of Astrophysics. I am a PhD student there. First of all, I would like to thank the organizers for giving me the opportunity to present my work here. Thank you. And this is the work on the galactic outflows in the cluster environment. So we have done a case study on Abel 2199, which is a cluster which has not reached dynamical equilibrium. Yeah, so you all know that the galaxy clusters are the ideal laboratories to study the galaxy evolutions, because when the galaxy is in fold, they will undergo certain morphological changes as well as they trigger the activity that could be ASIAA or the star formation. So moving forward. So there are the many galaxy evolution mechanisms which can change the morphology in the cluster environment. There are many mechanisms are there. So these are already have been discussed in the first session. So the one I want to discuss in this particular talk is ASIAA and stellar feedback. So ASIAA and stellar feedback can cause the outflows. This outflow can be either star forming due to the supernova or the stellar feedback, and the other one is the ASIAA, which are powered by the ASIAN wind. So why I have been interested in the outflows? Because outflows can give the negative feedback, which can decrease the star formation, and they can also enhance the star formation by positive feedback, and they have a different mechanisms are there. Regarding their structure, they can be at the nuclear scale or they can be extended up to the galaxy scale, and they can be biconical with the nuclear scale as well as galaxy scale. So the key question I want to answer in this question, not answer, like I want to study in this talk is that how do outflows behave in the cluster. So what we know and what we don't know about this outflows in the cluster environment, basically what we know about the ASIAN interaction, there are many studies, I am listing one of them. So where they have studied the ASIANs in the cluster environment as well as in the field galaxies where the ASIANs are there, and what they found, near the center ASIAN fraction is high, and as we move to outside the cluster in the intermediate region, so they show that there is a sudden drop in the ASIAN fraction, and after in the outskirts there is again sudden rise that might be due to the different fueling condition, like the galaxies are entering in the outskirts from the cluster. But for the outflows, which can be ASIAN driven or maybe the starburst driven, we need a few systematic case studies to see how the outflows behave within a cluster environment.
So what kind of ASIAN are these?
So this is an optical ASIAN detector by PPT. I will come to that. So to study this, our main focus is a Abel 2199 cluster. Why this cluster? Because this cluster has a rich data, IFU data, because I want to study the outflows using IFU data. And this cluster has not reached its dynamical equilibrium yet, so still the interactions are going on. Because ASIANs can be triggered by the interaction, so that's why this cluster is a good case to study the this outflows. So this is the motivation behind this work, to study how the outflows will behave inside the cluster with respect to cluster centric distance. So this is the basically the cluster, which is around 578 cluster members, which are confirmed by Song et al. And these all are confirmed using the spectroscopic redshift. And they have also classified further into the galaxies which are part of the groups in the cluster and the other which are isolated. But our motivation is to see how many IFU like manga data is available for this cluster, and what we check, we cross match this galaxy with the STS manga data. Manga is a IFU data of nearby. They have almost studied like catalog of nearly 10,000 galaxies for which the IFU data is available. We cross match it with it, and we found that nearly 102 galaxies which are part of the cluster, they are in this cluster. Like we want to study further this galaxy, and our motivation is to study the outflow. So for that we follow the detection strategy to detect the outflows in the cluster. So what we did, first we prepare the RGB image, which is this is a emission line RGB image. We choose 3 lines and 2 line, which is like with that we can detect the shocks. H alpha, which is for the star formation, and O3, which is for the ASIAN life of activity. So you can see that with this emission line we can see what part of the galaxy is emitting what kind of emission to study in a detail like what is happening inside the galaxy. So second thing we check like how many like what is the center source of these galaxies. To detect that we use a spatial BPT map, and this is for IFU, like this is a spatial BPT map for the manga one of the galaxy I'm showing here, and we want to see whether it's a star forming, composite or liner or CFET. Using IFU, and what we did, we used the STS fiber spectra also to confirm whether the center source is matching well with the IFU or not, and what we found it's matching well. So for all the galaxies 102 we check the nuclear region, what is that. Further we check the ionization dispersion relation. What is this relation? Look, on the x-axis it's N2 by H alpha. N2 by H alpha is dedicated to the like how the ionization is behaving there. If it's more, it means it's highly ionized. If it's less, it's less ionized. And the sigma H alpha will give us a dispersion in the velocity, like how much it is going away from. So if the ionization is more and dispersion is more, it is associated with the outflow, because outflow shows the more dispersion and they are highly ionized. But this could be due, if it's associated with the ASIAA outflow, there could be a more, and if it's star forming, there will be a less dispersion and less ionization. So what we did, we divided the depending on this red line, which is K01 line, below one are the star forming and above one the ASIAN spectra, and we check the correlation. And if the correlation or some anti-correlation is present there, means something is there that could be outflow or something else, but we have to check that. And what we found that nearly 41 galaxies which shows either correlation or the anti-correlation, means this could be the candidate for the galactic outflow. So we want to study these galaxies in the further, like what is happening with these galaxies. So first we prepare the RGB emission line images for all of these galaxies, and then we check the cross correlation function. Cross correlation function is see that how much the galaxies, like if there is an outflow, how much asymmetry in the line, H alpha line in their case. So you can see that this is, if the outflow is there, you will see that asymmetry in the line. If it outflow is not there, then it will be properly Gaussian will be there. There will be no asymmetry in the line. So in this way we use this method, like we horizontally we cross the like peak into different intensity level and prepare the map for the each pixel. Each pixel we check the spectra, and then we fitted the H alpha line like to check how much asymmetry in the line is there, and then we prepare the map, and then using that map we check the how much asymmetry is there, then we calculate the 90th percentile of the asymmetry in that, which will give the W90 map. W90 map basically gives us how much asymmetry in the galaxies. You can see that the asymmetry associated near the nuclear region. So after that we measure the velocity associated with all of these regions using the like velocity width by fitting the H alpha line with the narrow as well as a broad component to see how much is the velocity width there. And further we estimate all the parameter, along with we also check the what is the morphologies of these galaxies, what is the local environmental density of these galaxies, as well as the specific star formation of these galaxies. So then we check what's the trends in the asymmetry. What we found that the galaxies which are the ASIAN hosting, they have a more asymmetries as compared to the star forming, and the composites are in the middle of them, and also they have also velocity width in H alpha velocity width also increases in that format that ASIANs have a higher velocity width, means ASIANs are causing high asymmetries. Further we check the cluster-centric variation, like for the galaxies which show the anti-correlation, correlation. But we found that the galaxies which have anti-correlation, they are more near the center, and they decreases as we move outward, and also we found that the asymmetries are more near the center. This might be causing due to the ASIAN, and because the ASIAN fraction is also high near the center. Further we check their properties, and what we found that it's almost peaking near the intermediate region. This might be because of the transition, like where the galaxies are transitioning here. And then we found the anti-correlation galaxies. We don't know about the physical origin of these galaxies, why these galaxies shows a negative slope, like for a low ionization they have a high velocity dispersion, but the higher ionization have a less velocity dispersion. But what we found about these galaxies have a low momentum but a high velocity associated with them in the asymmetric region. So for that, what we in the literature we checked that there is some of the galaxies like I2 quasars as well as the red geysers, which shows this kind of properties which resembles these galaxies. But we are not sure like what is the physical origin for these galaxies, like whether they are just dispersing the medium downwind or anything else is happening. So another thing we checked the depending on the star formation rate and their velocity as well as their environmental density, we check how their correlation type, morphology, and the nuclear region is behaving within a cluster. And one of the thing I want to focus on that, what we found that the galaxies which are in the quenched region, they show a higher outflow velocity, like asymmetric region have a high out velocity there as compared to the others. And and others we found did not find any much correlation, they are almost scattered there. So with this I will stop here with the takeaways, like this is what we found. Thank you.
Thank you for being on time. Any questions or comments?
Thank you. I'm curious, what do you think would be the cause for the higher concentration, higher fraction of agents toward the cluster center?
There are many papers which suggest that the agent fraction would be high due to the interaction. Like when near the center of the cluster, there are many tidal interactions that could happen, which can lead to the agent triggering of the agent. So that could be the cause for that.
This is for one cluster.
This is for one cluster, but we have this is the one case study, and we are working on a Muse data for a large sample of cluster on 4 clusters to study how it will behave within that cluster.
Any other comments or questions? Teddy?
So quick question. So L2HR ratio depends on the metallicity, right?
Yeah.
And the metallicity depends on the mass. So how did you correct for this effect?
Can you repeat? N2 by H alpha associated with the metallicity. No, N2 by H alpha associated with the ionization. How much it is ionizing. To check the metallicity, we need a O3 or something, not iron lines or something, iron lines.
Well, let's
Maybe.
yeah.
Well, I have 2 quick questions, and so it is all based on the optical data, right?
Yeah.
You were including your star formation rate estimation. Do you have any concerns about like dust obscurations or things like that?
No, the star formation rate we have, it is not from the optical only.
Ah.
It is from the SAD fitting.
Okay, yeah,
Using
yeah.
14 wavelength band from UV to IR.
Yeah. And just to follow up Yenting's question, so you are working on different clusters, and can you comment on, I might have missed at the beginning, but what is special about this cluster?
Because there is a case study which says that the interactions can trigger the aging, and this cluster has not reached its dynamical equilibrium, means still the interactions are going on. So that's why we choose this cluster, and also this cluster has lots of IFU data available. That's why we choose, because we need IFU data to study these lines, like to do the spatial mapping.
You think the trend that you are finding can change with cluster properties?
Yeah, it can be changed. That's why we will extend this study to the further clusters.
Okay.
Thank you.
Last chance? Nobody? One more? Okay.
So your study relies on the manga selection.
Yeah.
Then do you think that will affect any of the conclusions?
Yeah, so actually the manga data is available for this cluster. It is spanning whole cluster, so it might be changed. So that's why we have to check for the other cluster, like whether it's a one cluster property or it is falling for whole clusters. Thank you.
Okay, if there is no more question, let's thank Chandan again. And our next speaker is